Welcome to lecture number 2. We're going over review number 2, integer exponents and scientific notation. Alright, so the first one we have is simplifying expressions with zero and negative exponents. Once again, exponents are those sort of little floating numbers up at the top. So we have b to the 1 power. What would that be? Well, anything raised to the 1 power is just going to be itself. So whatever the number is, b. For example, 5 to the 1 power would just be 5. Now, b to the 0 power, well, anything raised to the 0 power is going to be 1. It's a little odd, but that is what it is. If you ever want to know the answer to that, you can go ahead and shoot me an email and I'll send you the explanation. But so anything to the 0 power is 1. For example, 1,000 to the 0 power would be 1, just as 0.000 to the 0 power would be 1. And lastly, we have a base raised to a negative exponent. Now this one is weird, and when I was going through school myself, I had a friend explain this one to me as fish out of water. Here's a little tale I'll tell for you. So, if you caught a fish and you pulled it out of water, it would be an unhappy fish. It'd be a negative fish, right, if it was out of the water. Well, the question is, how do you make a fish happy? Well, to make a fish happy, you'll put it back in the water. So if you imagine the fraction bar as being the water line, putting the fish back in the water will make it happy. Okay? So, sort of a nonsensical story, but if you liked it, I'm happy. If not, just erase it from your memory. Okay, so what it's saying is, if you have a negative exponent, put it underneath 1 or put it in the denominator. Another way to say it is take the reciprocal. Okay? For example, let's say you had b to the negative 2 power. To fix it, or to make the fish happy, you would do 1 over b to the 2nd power. Okay? Take the reciprocal. That is if your exponent is negative. Okay, one thing to note, you are not allowed to have negative exponents ever, except for one case. The only time you're ever allowed to have negative exponents is if you're working with scientific notation. Other than that, you must always have positive exponents. Okay? All right. So let's go ahead and simplify these. First example, 2xy to the 0 power. So this is saying the whole thing is raised to the 0 power. Well, anything raised to the 0 power is just 1. And that's my answer. Regardless of what the thing is, if it's raised to 0, it is 1. Now let's take a look at the next one. This is saying the entire base raised to the negative 1 power. Well, fish out of water opportunity here. Go ahead and put that whole fish back in the water. And now the fish is a nice, positive, happy 1. Which, because it's just a 1, we'll go ahead and rewrite it just as 2xy. We are done, remember, with boxing our answers. Alright, next one. Oh, this is interesting. This time, we have a negative underneath the 1. This is weird. Well, what we're going to do is take the reciprocal. So I have that 1 over 1, and then what's the reciprocal of p to the negative 2? This will be 1 over p to the 2. But now wait a second here. We have a complex fraction. We're not allowed to have this. How do we simplify it? Well, what this is saying is we have 1 divided by 1 over p to the 2nd power. So let me go ahead and rewrite this. We have 1 being divided by 1 over p to the 2nd power, which now we have a division of 2 fractions. Now you might say, wait a second, that's not a fraction. But I can make it a fraction by just putting it over 1, which you can do with any number. Alright, so we have that fraction 1 over 1 divided by the half, or the 1 over p to the 2nd power. So to solve this, we're going to go ahead and change this to multiplication. and take the reciprocal, as we always do with fractions. All right, and then multiplying this out, I get p to the second power over 1, which is p to the second power. And that is my answer. Once again, if you have any questions on any of these sort of in-between steps, like how to do the multiplication of fractions, please let me know, and I'll send you either a video link or some other form of assistance. Okay, let's take a look at D. All right, well, I'm only trying to simplify here, and the only thing I see out of place, well, actually, there's only one thing I see out of place, and I want you to try to take a second and try to figure out what you think is the thing that's out of place. All right, it's that -8. What did I say about exponents being negative? We're not allowed to have them. Okay, so that's the only thing that needs to be fixed here. So go ahead and take that reciprocal. There we have it. And that's still being times by the y to the second power. I'll go ahead and put the 5 and the y to the second power over 1. It looks really hideous. Let me rewrite that. So that was 5 over 1 times 1 over x to the positive 8th now, times y squared over 1. Go ahead and we can multiply across the numerator, and we get 5y squared. And then we can multiply across the denominator, and we get x to the 8th power. And that is my answer, the simplified version. Alright, so now we're looking at how to apply the properties of exponents. Okay, really key important things here. Properties of exponents are pretty much going to always be around in math. They show up all the time. So these are important properties to have memorized. Okay, so here we go. First property, b to the m times b to the n. Well, notice the bases are the same even though the exponents are not. So how do we do this? Well, what you do is you keep the base and then you add the exponents, and you'll get your answer. Alright, so the next one is kind of similar but has a different twist. Once again though, notice the bases, b, are the same. The thing that's different are the exponents. So when you have that fraction and you have two items that have the same base, what you can do is you keep the base, but this time you subtract the exponents. And please note, you'll never switch it. It's always going to be the top value and subtracting away from it the bottom value. Alright, and then we have this next rule, which is called the power rule. Okay? So different than this one you have addition. For the power rule, you have b to the m raised to the n power, and what you do is you do b, m, and you multiply that to the n power. Okay? So power rule, I like to think of it, he looks like he's a little Superman with this little cape going on here. Superman's awesome, he must have multiplication over addition. I don't know, some sort of nerdy way to memorize it. That's how I did it. Okay, so power rule. That's kind of the one that has the name. Alright, and the next one we have, well, we have a new guy in this game. We've got a. So we have a and b, they're different. But notice they are being multiplied together, and they're being raised to the same power. So we can call this sort of the distributive rule of exponents. It only works if we have multiplication. Please note this. This is where a lot of students get confused. This works if we have multiplication, not if we have addition or subtraction. Okay? You cannot do that distributive rule with addition or subtraction. That is a big nope. Please do not do that. But it works if you have multiplication. Yay, happy teacher. Okay. My little rant aside, go ahead and erase that. Please remember that though. That little distribution works when you have multiplication. So that'll be a to the m power times b to the m power. You sort of distribute that power to both of the base items. The next property we have is a to the m divided by b to the m. very similar to this one down here. What you do is you just sort of end up distributing the top item, or the power, to both of the bases, or all of the bases. That'll be a to the m over b to the m. And then we have b to the 0, which remember, actually go ahead, pause the video, try to see if you remember what the last three are. Alright, so hopefully you wrote these down. That should be a 1, a b, and a 1 over b to the n for fish out of water. Okay, good things to have memorized, very important. Let's go ahead and take a look at the second example. Simplify the expressions containing exponents. Now this is a sneaky one. They all have the same base, so I might be really tempted to go ahead and just write down that 1 and add up all the exponents. But cannot do that. Why can't we do that? The reason here is because of that addition going on. Okay, that little adding item that we had up here only worked when there was multiplication. So we can't just add up their exponents because there's addition in between them. Shucks. But what we can do is just simplify with the exponents. So 1 to the 1 power, that's just going to be 1, plus 1 to the second power, well that's going to be 1. Let's see, 1 to the second power is 1 2 times. 1 times 1 is just 1. That'll be 1. And then 1 to the 0 power is going to be 1 again. Oh, interesting. Plus, let's see, 1 to the negative 1 power. What's that going to be? 1 to the negative 1 is, we take the reciprocal, 1 over 1, which is just 1. That's so weird. They're all turning out to be 1. And lastly, we have 1 to the negative 2 power. 1 to the negative 2. Let's see, that's going to be 1 over 1 squared. That'd be 1 over, well, what is 1 squared? 1 squared is going to be 1 times 1, which is just 1 again. Then 1 divided by 1 is just 1. Whoa, this is so strange. 1 seems invincible to any power you throw at it. It's like the ultimate avenger. Okay. Alright, let's add them up. 1 plus 1 plus 1 plus 1 plus 1 is 5. And there we go, we simplified this. So 1's a rather neat number because a lot of the times, the exponents don't do anything to it. It just comes back as 1. Alright, let's take a look at another example. We have 3 to the negative 2 power plus 1 over 9 plus p to the 0. Well, let's see. 3 to the negative 2 power, we have to get rid of that negative, so we use the fish out of water rule. That'll be 1 over 3 to the second power. Plus 1 over 9. There's nothing we can do to that one. It doesn't have any exponents. And then plus p to the 0. Let's see. P to the 0. Well, anything to the 0 is 1. That's going to be 1. Okay, let's go ahead and simplify. Right here, the 3 squared, which is going to be 1 over 9. Plus 1. Let's see, 1 over 9 plus 1 over 9. Well, these guys have the same base. I can go ahead and add them. Let's go ahead and add the numerators. So that's going to be 2 over 9 plus 1. Which, okay, and notice I'm going to do this. This is drawing an arrow, remember? So for drawing an arrow, if your work is not going to continue going downward, to let the teacher or whoever it is reading your work, to let them know where you're going, just go ahead and draw an arrow to let them know. So your work is nice and legible for grading or any other purpose. So 2 over 9 plus 1. Rewriting that, I can do 1 plus 2 over 9. Nothing happened. Once again, that's just addition. It's okay to write it like that. And then I can simplify this to the shorthand version, which is 1 and 2 ninths. These two are the exact same thing. The bottom one is just the shortened or shorthand version. So 1 and 2 over 9th. Okay, let's go ahead and work on example C. Okay, so whenever I see a large parentheses with lots of things in it, I always like to see if I can simplify what's inside first. So let's see, are there any common bases inside? Well, I have two A's, and I also have two B's, so I know I can use the quotient rule to simplify those guys. And then, I also notice the 14 and the 2. Those are both even, so I know I can simplify those. Alright, let me go ahead and write this out a little bigger. And then I'm going to go ahead and rewrite what's inside into just the fractions being multiplied together, which I'm able to do. Okay. Alright, so let's see. Well, simplifying, 14 divided by 2 is just going to be 7. And then I have the a to the second power divided by a to the fifth power. So I'll keep the base and then I'll subtract the exponents. So 2 minus 5. And then I'll multiply that by the last one, which is going to be keeping the b as the base, and then subtracting the exponents, the 7 minus the, oh gosh, what's the exponent there? Well, don't worry, if you don't see an exponent, it's actually going to be 1. Okay? Not 0, it is 1. So that's going to be 7 minus 1, all raised to the negative 2 power. Okay, so let's say we have 7, a to the, let's see, 2 minus 5 is going to be negative 3, and b to the 7 minus 1, which is going to be 6. So it'll be to the negative 2 power. You might be interested in putting that in the denominator, but first let's go ahead and work with, after we've basically simplified the inside, let's bring in that negative 2 using the distributive property because, notice, they're all multiplication. Alright, so now we have 7 to the negative 2 power times a to the negative 3 raised to the negative 2 power times b to the 6 to the negative 2 power. Alright, we can go ahead and simplify that. That'll be 7 to the negative 2 times a, let's see, power to power rule. That is negative 3 times negative 2, which is 6, times b to the 6 times negative 2, negative 12. Alright, once again, here I am using my arrow to let you know where I'm going with my work. I'll rewrite this, so 7 to the negative 2, a to the 6, b to the negative 12. Alright, so now let's go ahead and lastly deal with those negatives. We need to get rid of them. Okay. So let's take the reciprocals. We have 1 over 7 squared times a to the 6. And I'll just put that over 1 times, taking the reciprocal, 1 over b to the 12. Alright, lastly, let's go ahead and multiplying across the top and then across the bottom. We'll get a to the 6 all over 7 squared b to the 12. And let's see, there are no bases the same, no negatives, we're good. We have simplified. Okay, so there are different ways to simplify this problem, and if you know of different ways that you've done before and you end up with the same answer, you may go ahead, by all means, continue solving that way. As long as your work is neat and it makes sense. Awesome. Alright, so now let's look at the last thing, scientific notation. So by definition, a number expressed in the form of a times 10 to the b power, where a is between 1 and 10 and b is an integer, it is said to be in scientific notation. Alright, it said scientific notation because most often this notation is used in scientific problems. So let's go ahead and work with this. But one thing to note, when you're asked to write in scientific notation, take a look at this x here. That's the multiplication symbol. So, a lot of times we use the multiplication symbol as the dot. But for scientific notation, the dot is not considered acceptable. Please use the multiplication symbol, the original one. Okay, so that's just a side note. So hopefully, as again, these sections right now are just review. So if they're not quite review and you need some extra help on it, please go ahead and reach out to me. But so let's see. Once again, we want to try and get this number to somewhere between 1 and 10. So to do that, we're going to move the decimal as many times as needed until we succeed. So I'm going to keep moving my decimal over until, aha, I found a number, 2.302. That number is between 1 and 10. So I'll go ahead and write that number down, 2.302. Now, how many decimal places did I have to move to get that number? Well, 1, 2, 3, 4, 5, 6 places. So we moved it 6 places, which means I'm going to write 10 to the 6th power. Now, once again, I mentioned before, you're allowed to have a negative value for scientific notation. So what is the difference between a negative and a positive? Well, the way I like to remember it is if your value on the top is positive, we're going to think of money here. When the number on the top, the exponent, is a positive number, this is telling us the original amount was large. It wasn't a decimal. So think in general with your bank account. If you have a large number, it's positive, right? But if you had a negative number, that's sort of a sad negative experience to have negatives in your bank account. That's going to be small little numbers. So way to remember it. If you have a positive exponent, that means your original number was big. That's a positive check to see. If you had a negative exponent, that means your original number was a small, little, teeny decimal, which is not very fun to see on a check. Okay. But remember, this was originally a big number, which means that's going to be a positive 6. So that sort of leads me into our next problem here, which is actually a small decimal. But as usual, our plan is to move the decimals many times until I get a number between 1 and 10. So here's my decimal. I'm not going to be moving this way because that means my number is getting smaller. So I'm going to move the other direction. 1, 2, 3. Aha! I have gotten a number, 4.56. I'll write that down, 4.56 times 10 to the, well, how many decimal places did I go? 1, 2, 3. So I went 3 places, but then the question is, should that 3 be positive or negative? Once again, let's think, what was the original number like? If it was a big number, my exponent should be positive. If it was a decimal, my exponent should be negative. Well, it was originally a decimal, which you would not want to see a teeny decimal like that on a paycheck. I would never like to see that. So because it's a teeny number, that's going to be a negative. And there we go, my answer. Written in scientific notation. So now, another way to work with scientific notation is to actually get it out of scientific notation and write it in standard notation. Alright? So standard notation is how you would standardly write numbers. For example, you would never see this amount written on someone's check. That would be really strange to write that on a check amount. We're going to go ahead and translate this. First thing I like to do is check the exponent. That's a positive 2. Since it's positive, my original number was not a decimal. It was big. Okay, so 3.1. Oops, the 3.1 was a big number, which means I'm going to move the decimal to make it a bigger number, which means I'll be moving it to the right. How many times? 2 times. 1, 2. However many spaces I moved it, I'll just fill in those gaps with a 0. So my answer here is going to be 310. So this will equal 310. So the next one. Once again, I take a look at the exponent. It's a negative. Well, since it's a negative, that means my original value was a decimal. Okay, so my original value was a decimal. So what I'm going to do is I'll move my decimal to the left. How many places? 6. So 1, 2, 3, 4, 5, 6. Once I've done that, I'll go ahead and fill in the empty spaces with zeros. And there we go. So my answer is 0.000002. Please note, the 0 here is needed. I will be looking for that on your answers for your exams, definitely please make sure to put those in. Okay. Do not just leave it as point and then all your zeros. The reason is, I'll give you a good example. Let's say a nurse wrote on a chart 0.5 milliliters of, I don't know, some random medicinal amount. But let's say the next nurse who picked up that chart, the decimal point was so teeny she didn't notice it. So she thought she was supposed to give 5 milliliters. That is definitely a difference between 0.5 and 5. That could actually kill somebody, depending on what the medication was. But if the other nurse had written 0.5 milliliters, and when the new nurse came along, she couldn't see that decimal point, but she saw the 0.5. So, being clever, the nurse would think, okay, I know there's got to be a decimal there somewhere. So she'll just call on the other nurse and try to figure out where the decimal was, and the nurse would say to her, oh, it was supposed to be right there. My mistake. Okay, but that's just a good example for why you should keep the 0 in front of the decimal. I recently had an example with that when we were looking for the fireworks permit for New Year's. My mom was reading it, and she thought you needed a $59 down payment for the processing fee for COVID. Not a down payment, it was a processing fee. She thought it was supposed to be $59, and she thought that was insane. So I asked my mom where the decimal was, and then she looked a little closer on the paper, and she noticed the decimal was right there. So, if there had been a 0 in front of that, and my mom hadn't noticed the decimal, she would have thought there's something wrong with that number, so there must be a decimal somewhere. So she would have looked a little closer. Okay, so just another example. Happens in real life. It just happened a little before New Year's. So, all that long thing to say. Please put the 0 in front of the decimal. Thank you. You never know whose life it might save. All right, last example. A light year is the distance that light travels in 1 year. If light travels at a speed of 6.7 times 10 to the 8th power miles per hour, how far will it travel in 1 year? And that is given as 8.76 times 10 to the 3rd. All right, so to find the answer here, we're going to go ahead and work with the fact that distance equals rate times the time. That's supposed to be a nice R. It was not. All right, so the question is, what is the rate? Well, the rate is normally the miles per hour, which we have right here. So we'll go ahead and put that in. The rate is 6.7 times 10 to the 8th miles per hour. And then the time. What is the time? Well, we have it right here. 8.76 times 10 to the 3rd power. All right, so what we're going to do, go ahead, I'm going to ignore the units at this time. Ooh, that was more than I wanted to ignore. Let me go ahead and rewrite that. Okay. So then we're going to go ahead and regroup the decimals together and then the tens together. So we have 6.7 times the 8.76. And yes, we can do this because it's all just multiplication. All right, so multiplying the 6.7 times the 8.76. We're going to go ahead and just use a calculator on this on the side. Once again, though, on your exams, you should be doing everything by hand. So for your exams, you would not get numbers quite as odd as this. They should be easily done by hand or in your head. Okay, so multiplying that out, we'll get 58.692 times, well, let's see. We have 10 to the 8th times 10 to the 3rd. Keep the base, add the exponents. 8 plus 3 is 11. So we are very close to being done, but one thing to notice, it's very sneaky here, but this is not actually in scientific notation yet. Why not? Well, the reason is this number is 58, and remember, scientific notation, this number needs to be between 1, less than or equal to 1, and 10. So to do that, we're going to have to go ahead and change this into scientific notation. So let's take a look at the 58.692. We want to change that into scientific notation. Well, to do that, let's go ahead and move the decimal over until we get a number between 1 and 10. And we get 5.8692. But we move the decimal over once, so it's going to be 10 to the 1 power. All right, so now we can replace this amount with our newly created scientific notation, 5.8692 times 10 to the 1 power, and bring down the other 10 to the 11. And lastly, we can go ahead and combine these two to get 5.8692 times 10 to the 12th power, which is our answer. But this is a word problem, so let's answer in word form. So the question was, how far will it travel in 1 year? So the answer is, it will travel 5.8692 times 10 to the 12th miles in 1 year. All right, and there we go. That is our answer.